Good morning to all. Today we are discussing about reflection and refraction. Consider a discontinue in path of traveling waves. Example, junction of a overhead line and a cable whose surge impedance are different. Some adjustment in the voltage and current waves must take place such that the proportionality between the voltage and current is maintained. This calls for two sets of new waves to be initiated. First one, reflected voltage wave accompanying current wave that travel back the line superimposed on the incident wave. Second one, a set of refracted wave that penetrates beyond the discontinue at the discontinue voltage and current are continuous. Let ZA and ZB, the characteristics of impedances of the paths meeting at the discontinue with ZA greater than ZB. V1 is the magnitude of setup wave approaching the junction and I1 accompanying current wave. Then I1 is equal to V1 divided by ZA. Equation 1. Let V2 and V3 be reflected and refracted waves. The corresponding current waves are I2 is equal to minus V2 divided by ZA. I3 is equal to V3 divided by ZB. Here I1 plus I2 is equal to I3. Continuity relationship at the junction V1 plus V2 is equal to V3. Substituting for the currents and eliminating V3, we get V2 is equal to ZP minus ZA divided by ZP plus ZA into V1. Then ZB minus ZA divided by ZB plus ZA is called the reflection coefficient. V3 is equal to V1 plus V2 is equal to 1 plus ZB minus ZA divided by ZB plus ZA into V1. V3 is equal to 2 ZB divided by ZB plus ZA into V1. 2 ZB divided by ZB plus ZA is called the refraction coefficient. Numerical example 1. Surge impedance of overhead lines ZA is equal to 400 ohm. Cable ZB is equal to 50 ohm. Incident step wave magnitude 300 kV. Compute reflected and refracted voltage current wave magnitudes. Solution. Incident wave I1 is equal to 3 lakh divided by 4000 is equal to 715 amps. Refraction coefficient 50 minus 400 divided by 50 plus 400 is equal to minus 0.78. Then refraction coefficient B is equal to 2 into 50 divided by 50 plus 40 is equal to 0.22. Traveling waves continued. Reflected wave voltage wave V2 is equal to 0.78 into 300 is equal to minus 234. Reflected current wave I2 is equal to minus 234,000 divided by 400 is equal to 570 amps. Transmitted voltage wave V3 is equal to 0.22 into 300 is equal to 66 kV. Transmitted current I3 is equal to 66,000 divided by 50 is equal to 1320 amps. The diagram will be represented for the before and after. So before V1 is equal to 300 kV, ZA is equal to 400 ohm, ZB is equal to 50 ohm, then I1 is equal to 750 amps. After that, V1 is equal to 300 kV, then V3 is equal to 66 kV, V2 is equal to 234, then I3 is equal to 1320 amps, then I2 is equal to 517 amps, then I1 is equal to 750 amps. The voltage penetrating into the cable, only 66 kV cable, sometimes used to protect equipment, just insert the section of cable between overhead lines and terminal equipment. Next one, energy conservation. Energy is conserved at the junction by initiation of secondary waves. Energy input to the line V1 square divided by Z watts. V1 I1 energy in the reflected wave. Refracted wave V2 square divided by ZA plus V3 square divided by ZB. That is equal to V1 square divided by ZA, then ZB minus ZA divided by ZB plus ZA whole squared. That is equal to 2ZB divided by ZB plus ZA whole squared. That is equal to V1 squared divided by ZA. Proportionality of voltage and current incident, reflected and refracted waves at the junction imply energy conservation. The next, extension of multi-line junction. Incident waves V1 and I1, reflected waves V2 I2, refracted waves V3 I3, V3 I3, etc. Proportionally for refracted, V3B divided by I3B is equal to ZB. Then V3C divided by I3C is equal to ZC. Proportionally for reflected, V2 divided by I2 is equal to minus ZA. Continuity for voltage, V1 plus V2 is equal to V3B plus V3C is up to V3N. Continuity there, current I1 plus I2 plus I3B plus I3C up to N the value, I3N value. These relationships are enough. Find out the reflected and refracted wave in terms of incident wave and the characteristics of impedances. Behavior at line termination, a short circuit. ZP is equal to 0 minus 1 refraction coefficient. Hence V2 minus V1, I2 divided by I2 is equal to minus V2 divided by ZA is equal to V1 divided by ZA is equal to I1. No voltage can be developed. Reflected voltage wave must be exactly cancelled our incident wave travelling wave. Let short circuit be applied. Line fed by the voltage source also neglect the line resistance. The fault current increasingly identify at the rate of voltage V divided by IL di by dt, where L is the inductance of the up to the 0.1 meters away. Boundary condition at the sources short circuit setup, reflected waves as shown in next. In the short circuit condition, the current high, voltage low. The first initial wave of the input voltage is equal to V. Then reflected voltage is equal to V2, V divided by Z0. And refracted wave is equal to V. Then refraction wave is equal to 2V divided by Z0. So the tangential angle is equal to T less than equal to tangential. Then 2T tangential angle is equal to T3 tangential angle. Then next, rise of current at the source end. The current increases ZV, Z0 every tangential seconds. That is I dt by dt. That is I di by dt is equal to 2V divided by Z0. Then 2 tangential angle is equal to 2V is equal to 2V LC squared. L by C whole square is equal to, which was a expected neglecting wave reflected. Energy conservation, energy into input to the line before reaching the short circuit end of the first term, VI into T joules. That means the tangential angle. The energy stored in the electric field and magnetic field. Before reflection, VI tangential angle is equal to 1 by 2 CV square plus 1 by 2 Li squared. After reflection, the energy doubles due to the current doubling to 2Vi tangential. The energy stored entirely in the magnetic field as the voltage 0, 2V tangential is equal to 1 by 2 Li squared, 2I squared is equal to 2 Li squared. Hence, energy stored in the magnetic field after reflection is equal to 4 into energy stored in the before reflection. Here the open circuit, the voltage will be high, the current will be low. Here the voltage dominations of applied voltage is equal to maximum voltage into compared to the short circuit voltage. Then reflected waves to the current, then I less than is equal to tangential angle, then tangential angle T is equal to 280T, then tangential angle T less than is equal to 380 tangential angle. Traveling waves continued. Open circuit energy conservation by the time initial current and voltage wave arrive at the far end, and energy will VI tangential will have been fed to the line from the source. Half this energy will be stored electric 1 by 2 CV squared, magnetic 1 by 2 Li squared. Field is each. When the reflected current from the open circuit sources line current to be 0. In the absence of any dissipation mechanism, the energy is converted into electrical energy. The electric field must be contain energy in the incident and reflected waves. This accomplished by doubling the voltage which quadruples the energy stored in the electric field. Energy proportional to the V squared, the voltage surges can every destructive effect of terminal equipment. The doubling effect is therefore practically important since the doubles the potential of the wave. The next, reflection of a short circuit rectangular pulse short circuited at the end of the line terminated at the capacitor. A is equal to 1 by C of S equal to minus ZA divided by 1 by C of S plus ZA. Assuming the step incident V1 divided by S, V2 is equal to V1 divided by S equal to into 1 by C of S minus ZA 1 by into 1 by C of S plus ZA. That is equal to V1 divided by S alpha plus A divided by S plus alpha minus S divided by S plus alpha is equal to alpha is equal to 1, that is C into ZA. Then V2 T is equal to V1 1 minus 2 e power minus alpha t. Then V3 is equal to V1 plus 2 plus V2 is equal to 2 V1 is equal to 1 minus e power minus at. Then V3 is equal to refracted voltage. Traveling expression derived above the can be also derived using the Thevenin's equivalent circuit after the refraction the 2V. First diagram, it will be represented for before reaching the far end, little after reaching the far end. The next one is a refracted transmitted voltage as a function of time. The next reflection of a short circuit rectangular pulse short circuit at the line terminated in the inductor. As well as the same concept, there will be a voltage here in the current. In terms of operational impedance, the reflection coefficient A is equal to Ls minus ZA divided by Ls plus ZA. Assuming the step incident V1 divided by S equal to V2 is equal to V1 divided by S into Ls minus ZA divided by Ls plus ZA. Then V1 divided by S is into S minus beta divided by S plus beta. Beta is equal to ZA divided by L. V1 is equal to V1 into 1 divided by S plus beta minus beta divided by S plus S into S plus beta. S plus beta. V2 is equal to minus V1 1 minus 2 e power minus beta divided by the value of V3 is equal to V1 plus V2 is equal to 2 V1 e power beta t. V3 refracted transmitted voltage. The expression derived above can also derive the using Thevenin's equivalent circuit after the first reflection 2V1 and ZA. First diagram will be before reaching far end, little after reaching the far end. V2 of t is equal to minus V1 1 minus 2 e power minus beta t. Refracted transmitted voltage a function of time V3 of t is equal to 2 V1 e power minus beta t. Thevenin's equivalent apply Thevenin's theorem. across the x comma y to get the current through the voltage across the ZP, which is refracted voltage. Open circuit voltage across x and y. After removing ZP, after the wave arrives is given by V Thevenin is equal to 2 volt. Short circuit the source sending end. Impedance seen from x minus y. Z Thevenin is equal to ZA. Hence Thevenin's equivalent is 2 volt behind ZA. The current through the ZP is given by I minus I is equal to 2V divided by ZA plus ZB. Refracted wave V3 is equal to I into ZP is equal to 2V into ZB divided by ZA plus ZP. Note the expression within the parenthesis is the reflection and refraction coefficient. Recessive termination, if ZP is equal to R is equal to ZA, the reflection coefficient A is equal to 0, no reflected wave. The reflected wave V, incident wave. The incident wave is completely absorbed if there are no elements beyond the recessive termination. All energy contained in the incident wave dissipated in the resistance. Importance in communication circuit, little practice sufficient in power circuits. If R greater than ZA, energy that cannot be absorbed by R gets reflected. Thank you.